All right, hello everyone, welcome back to class and happy Friday. So we're going to get started. I don't have an announcement slide, but I also just don't have any new announcements. Keep in mind that the next assessment is next Friday, so a week from today, and then you have an achieve due on Monday. Those are really the main things. I have my normal office hour next Tuesday. We ready for class? Good. Okay, so chapter we are starting today is chapter 16, and this is all about acid-base theory. And I heard that you all have seen this before, a pH indicator in your lab. Yeah, so we'll talk a little bit about indicators, but this is just showing a blue solution that has some amount of acid or base present, and then that indicator strip tells us information about how much acid or base is in that solution. So this is our overview. I'm not going to go through that. But some things that we already know about reactions. Well, we know that we have reactants that form products. For a chemical reaction to occur, bonds must be broken or formed from the reactants, from those reactant molecules to form products. We start with one set of molecules and we end with a different set. In order for that transformation to be a chemical reaction, chemical bonds have to break or form. Otherwise, you're ending with the same molecules and nothing has changed. We talked all about reversible reactions last section. So reactions that are in equilibrium with the reactants and products. Those reactions proceed to reach equilibrium, and at equilibrium, both the forward and the reverse reaction happen simultaneously. And that means that at a given time, there is both reactants present and products present. And then we can use K to determine the favorability of reactions. So K is products over reactants. If K is greater than 1, the forward reaction is favored. If it's less than 1, the reverse reaction is favored. So in this chapter, we're going to keep all of that in mind, but we're going to learn about a specific reaction, which is acid-base reactions. And this is a just extremely common reaction. You're going to see this again in organic chemistry 1 and 2, in biochemistry if you take that class, and I'm sure in your biology courses you talk at least a little bit about acids and bases. So we're going to really dive into what these reactions look like and what happens in an acid-base reaction. Different types of acids and bases. First, we need to understand what happens when an acid is added to solution. So these reactions that we're talking about all happen in solution. And so you might remember this image from chapter 12, I think it was, when we talked about intermolecular forces. So this is the strongest intermolecular force where it's an ion-dipole interaction. So if you add an ionic compound like sodium chloride, which is a metal and a nonmetal that makes it ionic, it completely dissociates into Na plus and Cl minus. And so the cation, sodium, is attracted to the negative oxygens, the red in water, and then the negative, the cation, is attracted to the partial positive hydrogens in water, and so it dissolves in water. The same thing happens when you are looking at a strong acid that's added to solution. We have a list of strong acids that we'll get to. One of them is HCl, hydrogen chloride. When HCl is added to solution, it completely dissociates into H plus and Cl minus. So it's not an ionic compound because we don't have a metal and a nonmetal. We have two nonmetals, but it behaves like one where it completely separates into the cation and anion. So same thing, Cl minus is dissociated and is dissolved by the partial positive hydrogens. H plus is dissolved by and attracted to the partial negative oxygens. And then the same thing is true for the strong bases. Sodium hydroxide is a strong base. This is an ionic compound. We do have a cation and an anion, but it being a base, this ionic compound is a base because it produces that OH minus, the hydroxide ion. So we'll talk about defining acids and bases. But just keep in mind for now that strong acids and strong bases dissociate into ions in water, just like ionic compounds do. So we're going to talk all about acids first, and then all about bases. And there are three commonly discussed definitions of acids and bases. There is the Arrhenius definition, Bronsted-Lowry, and Lewis. We're talking mostly about Arrhenius and Bronsted-Lowry in our class, but we will discuss Lewis acids and bases a little bit. But based on the Arrhenius and Bronsted-Lowry theories of acids and bases, acids are the providers of the H plus ion. So we saw in that previous slide, HCl, that's a strong acid that dissociates into H plus and Cl minus. It's an acid. HCl is an acid because of the H plus, because it provides the H plus. Arrhenius definition specifically is that acids increase the concentration of H plus. When dissolved in water. And then Bronsted-Lowry acid definitions is that acids are H plus donors. So really two different ways of saying the same thing. H plus donors would increase the concentration of H plus in solution. So HCl again, this is one of the strong acids, produces H plus and Cl minus. Now that H plus is often referred to as a proton. So sometimes Bronsted-Lowry acids, instead of saying they are H plus donors, it will say they are proton donors. The reason we refer to H plus as a proton, so hydrogen, remember hydrogen is the first element in the periodic table. Its atomic mass is 1. It has 1 proton. And neutral hydrogen, if it has 1 proton, it must have 1 electron. And that's a hydrogen atom. Neutral hydrogen atom, 1 proton, 1 electron. But here we're talking about H plus, the transfer of H plus, or donating H plus. So we have hydrogen with a +1 charge. Then it must have lost an electron, so all that it is 1 proton. So H plus, a hydrogen without any electrons, is often referred to as a proton. H plus is highly reactive, so in solution, in an aqueous solution with water, it will bond to a water molecule to form H3O plus. So that's what is showing down here. Hydrogen ion or proton in water form hydronium, which is the name of this thing. We have H plus, it will bond to the oxygen in water. These electrons, non-bonding electrons, can actually create a bond and share that with hydrogen. And then we have this ion +1 overall charge, we call that hydronium. So H plus and H3O plus are often used interchangeably, synonymously. So you might see H3O plus sometimes, you might see H plus, but if H plus is present in an aqueous solution, then it forms H3O plus. So here's HCl Without H2O in the equation, we'd say it forms H plus and Cl minus. This is a balanced equation. But this happens in water. So if we include water in that reaction equation, then we have HCl and H2O. This would dissociate into H plus and Cl minus, but the H plus bonds with H2O, so we have H3O plus now, and then Cl minus. Now notice that when we're looking at an acid, the ions are on the product side, including the H plus. And the H plus, the production of the H plus is what makes this an acid. Going back to the previous slide, Arrhenius acids increase the concentration of H plus. So a really strong acid would increase the concentration more so than a weak acid. We're going to talk about strong versus weak acids and bases. So more H plus means stronger acid. So we've got 2 learning checks here. Let me talk you through these 2 questions and then I'll start it. But here we have particle pictures. We've got 2 acids, HA, which was added to water in this beaker, and HB, which was added to water in this beaker. The first question is, based on these pictures, which one is stronger? Which acid is stronger? And keep in mind, there are HA, HB associated molecules, and then you've got H plus, A minus, and B minus, the dissociated ions. And then the next question is on this next slide. Again, looking at which acid is stronger, but thinking about these as equilibrium reactions and then using K values. So we're still looking for higher concentration of H plus would be a stronger acid, but try to translate that to what we know about K. So remember that acids provide so the stronger acids would, when added to solution, create more Oh, it has to be associated from the other solution. Like it has to be just the gray one on its own. So like Oh, one more minute. All right, I will close it here. All right, this first question, we've got two acids, HA and HB. Add them to water, and remember that an acid dissociates into H plus and then the rest of the molecule, in this case, A minus or B minus. So I wrote out the equilibrium equations over here. The definition of an acid is that it produces H plus. So I know, since this is a question about acids, on the other side of the equation there will be an H plus, and then the other option, what's left is the A or B. And then we also know that acids are stronger if they create a higher concentration of H plus. H plus is this gray circle on its own. If H plus is if hydrogen is bonded to A, then you'll see them close to each other, which is not present in that beaker. But in this beaker, we have H and B still bonded to each other. So this is not an H plus ion. This is H bonded to B. Over here, all of these are H plus ions. Here we just have the one H plus ion. So with HA, that we know this one is a stronger acid because it produces more H plus. It dissociates into H plus and the purple A minus. Where this one mostly stays bonded as HB and then just has a little bit of H plus. So acidity is on a scale. This represents a strong acid that completely dissociates. This represents a weak acid that only sort of dissociates, partially dissociates. Questions on that one? Okay. The next slide, we have two acid-base or acid reactions. And we have K values. Both of these K values are less than 1. They're both pretty small. But remember that K, I hope this is like burned into your brain at this point. Concentration of products over reactants. And in both of these equations, the H plus, or in the first one, H3O plus, is on the product side. It's on the right side. So a higher K would indicate, larger K would indicate a higher concentration of H plus in solution. So here we're comparing the size of K, the magnitude of K. Larger K would mean stronger acid. So that's HF for this one. This K is larger. So let's say larger K, more H plus, stronger acid. So both of these in general are weak acids, but we can still compare weak acids to each other and say one, it can be stronger than the other, and that's what we're seeing here, because that K value is larger. So this K value is small, which tells us that at equilibrium, there is more reactant, so HF or HC2H3O2, present at equilibrium than the products. So these are weak acids, or we can say these equations are weak acid ionizations. Both of the equations here are weak acids. They don't go to completion, meaning not all of the starting material is dissociated into ions. And so these are always shown with an equilibrium arrow, which is the single arrowhead going to the right, single arrowhead pointing to the left. Now, strong acid ionizations, which are not represented on this page except for this reaction down here, is one of the strong acids. Strong acid ionizations go to completion, meaning that the H plus or the HNO3 completely dissociates into H plus and NO3 minus. These are often shown with a regular reaction arrow. So just one single arrow with the double arrowhead. Because we don't really say that these are in equilibrium, but I'll be honest, you'll probably see equations like this with an equilibrium arrow. I'm not going to grade either way, like it's fine with me if you have the equilibrium arrows here, like I'm not going to mark that wrong. I might leave feedback for you, but that's a small, really minor mistake. But I think it's more important to understand the reason why we have equilibrium arrow for weak acids and bases and the normal reaction arrow for strong ones. And that's because this one doesn't really exist in equilibrium. Because this is such a strong acid, it will just form those ions. And then it is very unlikely that these two ions will form the HNO3, will come back together to form HNO3. Okay, so let's look at this graph here, which demonstrates, based on concentrations, the difference between strong and weak acids. And we can classify acids as strong or weak, again, based on the concentration of H plus ions, or in other words, the H3O plus ion. Strong acids would have higher H plus concentrations, and then weak have low. So looking at these two graphs, we first have HCl over here. This, we've already discussed this as being a strong acid, and it is considered a strong acid because when it is added to water, it completely dissociates into H plus and Cl minus. So we have relative concentration or number of moles on the y-axis, and this is 0. Assuming this is added to solution, there are 0 HCl molecules still that bonded together. We have high amounts of H3O plus and Cl minus. So this would be consistent for any of the strong acids that we have listed over there. A weak acid would have much more of the original molecule present in solution than the ions. So there still are some ions present, but it's mostly in this associated form. So still the neutral molecule. This is why that K value was so small. We have really low concentration of products, but high concentration of reactants. So this list over here are strong acids with K is greater than 1. So more products than reactants at equilibrium. They are 3 halogens, but not chlorine. So chlorine, HCl, HBr, HI. And then HNO3, H2SO4, that's sulfuric acid, and then HClO4 and ClO3. So it is helpful to remember these, or when you're working with any acid-base reaction, you should consider if you're looking at a strong acid or a weak acid. Okay, let's go to this question here, this learning check. So first you'll write the ionization reaction for HNO3. Then determine the H plus concentration in 1.77 molar HNO3. Then write the ionization reaction of HNO2, and then consider how the H plus concentration, we have equal concentrations of the acids, but H plus in 1.77 molar HNO2 compared to H plus in 1.77 molar HNO3. So just this last question is the iClicker, but work on the whole page. When you get to the end, you can submit your answer for that. So you should work on the first three before working on the last one. Okay, I'll keep this open, but let's go through the first two. Then I'll give you all some more time to work on the last one. So the first question is to write the ionization reaction of HNO3. We should remember that this is a strong acid. It's going to give away an H plus, and then the rest of the molecule becomes negative. So we got H plus and then NO3 minus, a polyatomic ion. And then calculate the H plus concentration in 1.77 molar HNO3. Well, what's important to answer this question is that we know this is a strong acid that completely dissociates. So however many moles of HNO3 is added to solution, all of that becomes H plus and NO3 minus. So we can use coefficients and molar ratios to calculate the concentration of H plus, or we can think about that conceptually. If we have 1.77 molar HNO3 and all of that becomes H plus and NO3 minus, then we should have 1.77 molar H plus in solution. But to actually write that out in a calculation, we'd start with 1.77, I'm going to say moles of HNO3, that's what we're provided, per 1 liter. So just converting molarity to moles per liter. And then we use the molar ratio. We have 1 mole of H plus produced over every 1 mole of HNO3 added to solution. And then cancel out moles of HNO3, and we get 1.77 moles of H plus per liter, or 1.77 molar H plus. We can do that for a strong acid or a strong base, which we'll talk about soon. Because it completely dissociates, we can't use that equation for weak acids and bases, because not all of the starting material becomes the product. Okay, I'll give you another minute or two for the next 2 questions, and then we'll review them together. Let's see. 30 seconds and I'll close it. Okay, closing it here. 3, 2, 1. Okay. All right, so ionization reaction of HNO2, it's still an acid, so it still dissociates into, I'm going to wait on the arrow, but it dissociates into H plus and NO2 minus. I left out the aqueous, but all of these will be aqueous. The difference in the arrow is important here. This is not on our list of strong acids, so it does not completely dissociate. We need that equilibrium arrow here. So if you don't have the equilibrium arrow, erase what you wrote and add in the equilibrium arrow. That's important for weak acids and bases, because when this is added to solutions, some of it produces H plus and NO2 minus, but most of it is still HNO2. So keeping that in mind for the weak acid here, comparing the concentration of H plus in both of these, well, one is a strong acid where all of it converts to H plus, that's HNO3, and the other is a weak acid where only some is converted to H plus. So concentration of H plus from HNO2, I'm just going to write that as a subscript. What do you think? Less than or greater than? Less than, yeah. It's a weak acid, so it doesn't produce as high of a concentration of H plus as HNO3 does. Now like I said, we can't do that calculation for weak acids and bases. We would need to calculate the equilibrium concentration. We'd need more information, and we'd have to do an ice table, which we will do later in the chapter. Not today, though. Okay, any questions on these two, or this whole page? Okay. So we're going to shift to talking about bases, which is very similar, except for that instead of producing H+, they produce OH-. So this is just a reminder of that slide we looked at the beginning of class. The base is on the right. Sodium hydroxide dissociates into Na+ and OH-, increasing the concentration of OH- in solution, which makes it a base. So based on the Arrhenius theory of acids and bases increase the concentration of OH- ions in solution. So NaOH is a strong base. It fully dissociates, as we saw in the last slide, into Na+ and OH-. This OH- is the key part. The cation can change. We'll see that in our list of strong bases. But having that OH- ion is what makes that a base. And then just like acids, we have strong bases and weak bases. Weak bases are written in equilibrium. NH3 is a common weak base. So if NH3 is added to water, it will take a hydrogen from water. Then water is producing the OH-, but since NH3 took the hydrogen from H2O and became NH4, that makes NH3 the base. Because of NH3 being there, we can have the OH-. And then this particular example is an example of hydrolysis reaction, which is breaking water. One H2O molecule is broken into the OH- and the H+. And the whole reason we are worried about acids producing H+ and bases producing OH- is because if these two now bond together, they become water. So it's all really relative to water. We've got more H+, that means an acid was added, an acid produces the H+. More OH- would mean a base was added, bases produce the OH-. Okay, so again, strong and weak bases. Strong bases have high OH-. Weak bases have low OH-. And then we see the same observations here. Strong base NaOH. At equilibrium, no NaOH is present. It's all OH- and Na+. A weak base at equilibrium has a lot of NH3 and a little bit of OH-, a little bit of NH4+, which is NH3 with a hydrogen. And then we have the list of strong bases here. These are easier to remember. They are all hydroxides, so all of them have an OH- ion, the polyatomic ion. And then it's OH with group 1 metals, lithium, sodium, potassium, etc. Or group 2 metals, calcium, barium, strontium. So we have OH- in all of them, and then group 1 metals or group 2 metals. So again, this is helpful to remember, and make sure when you're solving problems, you consider whether you have a strong or weak base if it's a problem about a base. Okay, let's do this next question. So you are writing ionization reactions for potassium hydroxide, barium hydroxide, and CH3NH2, which is called methylamine, but you don't need to know that name. So let's do the first one together. Well, before I even write the arrow, let's think if it's strong base or not. Potassium hydroxide, we have the hydroxide ion, and we have a group 1 metal. So that makes it a strong base. So we should have that normal reaction arrow. And then these just separate into the ions. K plus, it's in the first column. First column metals often, or almost always, are a +1 ion when they are ionized. And then polyatomic ion OH minus. So barium hydroxide, that is also on our list of strong bases. You should go back and double check. So that ionization reaction will look similar to the first one, but a little bit different. This last one, CH3NH2, this is not on our list of strong bases, but one thing that I want you to remember is that if you have a nitrogen, and we saw this example with NH3, but here we have almost the same molecule, but CH3NH2. That's a sort of the Lewis structure. I just didn't draw the CH3, but for that last molecule. If you have a neutral nitrogen, that is capable of making another bond with a hydrogen. So nitrogen is neutral here with 3 bonds, but it could also have 4 bonds, no lone pair, and that would still have 8 electrons in its valence shell. NH4 plus is a nitrogen with 4 bonds to hydrogens. So nitrogens, neutral nitrogens, are weak bases. So consider when you're working on this, I'll give you a couple minutes to get started. Let's add H2O, because looking at this, we don't have any OH, no oxygen. This is not going to produce OH minus on its own, so let's add H2O for this one. Okay, I'll give you some time to work on those two. And then if you're ready, go to the second question to rank them by OH minus concentration. Okay, second one here, barium hydroxide. Barium's in the second column, so it will have a +2 charge. I know that because it's in the second column of the periodic table and those metals have a +2 charge when in an ionic compound. And I know that OH, hydroxide, has a -1 charge There are 2 of them in that compound, so -2 overall, so barium must have a +2 charge. So BaOH2 separates, ionizes into barium and 2 OH- ions. For every 1 barium hydroxide, we have 2 hydroxide polyatomic ions. And one thing I'll point out here, you may have noticed, maybe you didn't, but I have changed where I put the minus sign for hydroxide. It doesn't matter where you put it. I don't like putting it next to the number if there is a number, so that's why I moved it to the other side. But generally, I like having it by oxygen because oxygen is what carries the negative charge. If you were to calculate formal charge for the 2 atoms, oxygen has the negative charge. So it can be moved around, doesn't matter where you put it as long as it's there. And a superscript on either side. Okay, so that's our ionization reaction for barium hydroxide. For the last molecule, we're looking at bases and producing OH-. For H2O to become OH-, and I'm looking at H2O because this is the only one with the oxygen, it has to lose a hydrogen, and that hydrogen has to go to this molecule. And then I mentioned earlier that that nitrogen can accept a hydrogen and have 4 bonds. Just like when we saw NH3 becoming NH4. I'm going to go back to that. NH3 in water produces OH- and NH4+. This is a very similar molecule where we'll have CH3 NH3+, so 1 additional hydrogen that's taken from the water, and then the water is now OH-. Yeah. Yes, on the nitrogen. Yeah. Just to draw the structure for you. That's what it looks like at the top. So now the nitrogen has 4 bonds and it has a plus charge with 4 bonds. Okay, now the last question here. Let's say we have equal concentrations of all 3 of those bases and we're ranking the hydroxide concentrations in solution. Well, we already know that this last one is a weak base and the first 2 are strong bases. So if we have equal concentrations of all 3 of these in like 3 separate solutions, this will have the lowest amount of OH- because it's the only weak base here. So we know CH3NH2 will be the lowest amount. And then now we're comparing the 2 strong bases. Let's say we have 1 molar for all 3 bases. For every 1 mole of potassium hydroxide, 1 mole of hydroxide ion is formed. For every 1 mole of barium hydroxide, 2 moles of hydroxide ion is formed. So barium hydroxide would produce the highest concentration because for every 1 barium hydroxide compound, we have 2 hydroxide atoms. So potassium hydroxide and then barium hydroxide. Questions on this slide? Okay. All right, we'll be done. We'll continue this on Monday. Have a good weekend, everybody.